In our previous video, we went over a very basic review of light as a wave and light as a particle. So we talked about wavelength and frequency and speed. We also talked about the energy of a photon of a certain frequency of light. What we're going to be doing in this video is we're going to be using that concept to generate Bohr's model of the atom from his spectral experimentation. Again, you're going to need something to write with, you're going to need something to write on, and once you have those things ready, let's go. Okay, so if we take just what we consider to be white light, sunlight is an example of it, and we shine it through a prism. What we expect to see when we shine sunlight through a prism is we see a rainbow, right? A rainbow is a continuous spectrum, so one color bleeds into the next, and there are no gaps whatsoever. Bohr, when he did this with hydrogen gas, found a completely different result. When he took hydrogen gas and shone that through a prism, he didn't get a continuous spectrum. He got a series of 4 lines. Right? He got like a dark bluish indigo kind of line, he got a light blue line, he got a yellowish green line, and then he got a red line. So what this means is that these lines, these colors, correspond to individual wavelengths. And if we remember back to our wave equations, individual wavelengths correspond to frequencies, and those frequencies correspond to energies. Right? So Bohr's experimentation for this hydrogen atom was that he only got certain energies of light when he shone hydrogen gas through a prism. And when you repeat this with other elements, you get similar results. You just get these lines. It's just that the exact color and energy and wavelength of the lines change a little bit. So why did this happen? Well, one thing we have to look at is remember the idea that energy is quantized, right? So the lines correspond to the gaps in the energy states, the quantized gaps in energy states that the electron can occupy in the hydrogen atom. Right? So you have what's called your ground state, which is your low energy state, and then you have a higher energy state, which we'll call, for example, n equals 2. One that higher than that we'll call n equals 3. And the gaps between those states, the gaps between n equals 1 and n equals 2 is a line. The gap between 1 and 3 is a second line. The gap between 2 and 3 is a third line. Right? So in order to transition between those states, the atom has to absorb or emit, if it's going down in energy, a photon whose energy is the exact difference between those states. So that's what you're seeing in the emission spectra. You add energy in from your electrical source, it excites the electrons into higher energy states, and then when those electrons come back down to their lower energy states, they have to emit a photon of light. And that photon that you see is what gives rise to those individual lines. Right? So each of those lines is an energy gap between four transitions between allowable energy states. And if we bring up a diagram of this, we have the hydrogen line diagram. We have our ground energy state there at 1, and then it goes up to 2, 3, 4, 5, and it goes all the way up to infinity. Now, one thing to keep in mind about energy is that since we are dealing with an electron and a nucleus, since they are oppositely charged, this is going to be an attractive force. Attractive forces have negative energies. The more negative the energy, the more attractive the force is. Okay, so when we go up to infinite energy level, the energy is 0, meaning that there is no attraction between the electron and the nucleus. But as you go into lower and lower energy levels, that energy gets to be more negative because the attraction gets to be stronger and stronger. Right, and there are 3 primary series of lines that you can make out for the hydrogen atom. And you have the Lyman series, which are all the transitions that go down to the ground state, n equals 1. Those are all in the ultraviolet. Then you have the Balmer series, which is all the transitions going down to the second lowest energy state, so n equals 2. Those happen to be in the visible region. Right, so that gives you your indigo purple, your light blue, your greenish yellow, and your red. And then you have what's called the Paschen series, which is going down to the third energy level, and all of those energy transitions are in the infrared portion of our spectrum. Now, the equation I have on the right is Bohr's equation for the energy of each of the individual energy states. Right? So energy state number 1 is negative 2.18 times 10 to the minus 18th joules. Right? Because we're going to divide it by 1 squared, because 1's the energy number, so we get that back. The negative 2.18 times 10 to the minus 18th is the Rydberg constant. Right? So all you have to do to find the energy of a state is just plug it in with your n value, and you've got that. If you want to find the energy of the gap between them, just find the energy of the two states and subtract. Right? And then you can turn that energy into a frequency, you can turn that frequency into a wavelength, so you can actually predict all of these different series of lines. And Bohr wound up doing this, and he created his model where you still have the nucleus in the center. That hasn't changed from Rutherford's model. But now, instead of each electron orbiting the nucleus on its own path, the electrons will exist in their own individual shells, and the distance that a shell is from the nucleus depends on the energy of that shell and how much energy it takes to get down to the highest and lowest energy values. Right? So 1 is going to be the closest to the nucleus because it's the strongest attracted. 2 is going to be farther away. 3 is going to be farther away from that. And then what you're going to see is that the gap between energy states gets smaller and smaller and smaller the farther out you go. So the distance between the shells will get smaller and smaller. This diagram right here doesn't do a really good job of showing that because they want it to be more readable, but that's what you'll see as you go through. So like the gap between n equals 3 and n equals 4 is smaller than the gap between n equals 2 and n equals 3. So this is the Bohr model of the hydrogen atom. Now, this model is fantastic. It's what you guys used for freshman year bio. It still works really well for a lot of the things that it does, but there are some limitations. Right? The first and the most major limitation of the Bohr model is that it only works for systems that have one electron. The reason why is because when you add a second electron, you create this sort of classic three-body problem from physics because you have the nucleus as one particle, and then you have your two electrons, and it's extremely difficult to solve. The best supercomputers can get you good approximations, but even they take like 12 to 14 hours to get even the most basic approximation. Right, so that's one major limitation. It only works for hydrogen, helium plus, lithium 2 plus, and so on and so forth. So just single electron systems. Most atoms that we deal with have multiple electrons, so this doesn't work very well. It can only provide, at best, an approximation. The second major problem that its model has is that since we know the electron is negatively charged and the nucleus is positively charged, they should be attracted to each other. So why doesn't the electron just fall into the nucleus? Right? This is something that Bohr ignored from his model because he just said, well, yeah, it's just not going to happen. Right? But it's a good question because, if all we're talking about is attraction, it should at some point happen. And the other thing about this is that the Bohr model does not tell us anything about the physical properties of the atom. So, for example, it doesn't tell us why certain elements will be solid instead of liquid instead of gas. And one of the other ones that we're going to cover later in this chapter is why, for example, are certain elements attracted to a magnetic field and certain elements repelled by a magnetic field. None of this can be discovered through the Bohr model. Now, in the next video, what we're going to do is we're going to start the path to quantum mechanics. So we're going to start going to our current model, which is the quantum mechanical or electron cloud model. And we'll start talking a little bit about matter waves, we'll talk about uncertainty, we'll talk about the Schrödinger wave equation, and how that gives rise to all the different orbitals and what they look like, and from there how to fill those in to do electron configurations.